Yeah. Okay, thanks. Actually, the title of the talk is a slide a little bit blind.
Oh,
blind to
sorry.
you, but no, I just yesterday changed. So okay, let's see. Directed graph auto-encoders and quantum graph transformers. I muted myself and I unmuted this laptop here. Is that okay? I just want to make sure that people online.
Yeah, thank you.
Yeah, so okay, I know that the time is really limited, so I'll try to go as fast as possible. Actually, the talk is two parts. It's in one talk. The first one is direct graph autoencoders. The second one is some exploration of graph transformers on quantum computers. So I'll keep both parts short given the time constraint. So okay, so for the first part, right? The idea is that you are given a graph and you want to do link prediction, right? You have a directed graph and you want to predict links. And for both parts of the talk, really, the ideas are pretty simple. For the link prediction part, you just say the following, right? I will leverage the duality that is incorporated in directed graphs, and for example, the hits idea for ranking web pages, to encode and to create some embeddings, and then I will just decode by forming an approximation of the adjacency matrix by using the embeddings that I just computed during the encoding part, and I'll just apply the sigmoid function, and that would be the idea. So link prediction, right? So what you want to predict is you're given a directed graph and you want to say, is U connected with V? And if so, with what direction? Like, does U point to V or V point to V? And directed graphs are used in many applications. As an example, you can think of citations and citation graphs. Obviously, a paper that was written in 2020 cannot cite a paper that was written in 2024, right? And many interesting applications that come to light. I mean, of course, the undirected graph part is way more research, but this is starting to change. So yeah, about the algorithm that we're going to describe, and I'm going to describe really quickly. It's basically saying that its node points to other nodes, and it's pointed to from other nodes. So you basically try to break the embedding vectors into the so-called source vectors and target vectors, right? So when I point to you, I am your source and you're my target, right? So there are different embeddings for source and targets. And the idea comes from hits where you run web pages and you have hubs and authorities, right? Hubs show to web pages, and then authorities are being pointed to by hubs, right? So the name of the algorithm is direct graph autoencoder. You know it as DI. And okay, without further ado, so the hits algorithm, right? This is an algorithm that I think was discovered in the 90s or around the zeros. It basically created PageRank. It's hits is query based. It's a query based algorithm, right? So what you do is you input a query, you get some the seed set, you get some related web pages, and then you incorporate some more and you build a smaller graph, right? A much smaller graph than the original one, and then you basically try to say the following: which web pages are the hubs and which are the authorities. A good hub represents a page that points to many other pages, while a good authority represents a page that is linked by many different hubs. Kind of, again, PageRank does something slightly different, right? So an authority value is computed as the sum of the scale hub values that point to that page. So in other words, if three of you point to me, then you are the hubs, I am the authority, and I get the contributions from you, but I scale because three different web pages. So for me, likewise, a hub value is the sum of the scaled authority values of the pages it points. So again, there is a directionality. If I point to you, I am your hub, you are the authority, and then there are source and target scalars or vectors, if you like. So in the language of linear algebra, you can recover the sorts by doing the forward path, right? And you take the adjacent link and multiply it with the authority scores, and that's how the hubs are determined. And then you do the same with the transfer. So basically, outgoing links imply multiplication with A, incoming links imply multiplication with the A transpose. So now, high-level idea of what we're going to see, like we're not interested in ranking, we are interested in link prediction. However, for the first time in 2022, the paper that appeared at AAAI, the idea was to leverage ideas from kids for graph convolutional networks, right? For directed graphs. And we don't have having authority vectors, right? But we call source and target vectors for the link prediction problem. So if we were to enrich, let's say, a hits-like idea for graph neural networks, what would we do, right? I mean, we would replace the hub of authority vectors with learnable vectors, right? So this S, T, S, T, and T. S and T, or even one of them is just some initial bunch of future vectors, right? The initial embedding, and then TS and WQ are learnable matrices that are going to be learned by the neural network itself, right? So if you were to incorporate that in the previous slide, a hits-like approach would give your source is A times the target embedding times the learnable matrix WP, and then likewise the target. Now you cannot not add non-linearities and self-links to finalize the encoder part. So from here, you can go to an idea like a graph convolutional network, right? And you add self-links. That's the prevalent idea in graph convolutional networks. And if you know the non-linearity, I mean, by the rail loop, for example, by the graph again, you have basically exactly that. And here you see some matrices alpha and beta. And the idea from that comes from some recommender system work that we did earlier at IBM, where you basically have the cosine similarity, but then, I mean, you have the dot product similarity, right? But then the dot product is between two vectors of A and B. You have to take the norms, and then you have to take the other, right? So by scaling the norms by alpha and beta, you give different attenuation factors to the angle versus the magnitude and vice versa, right? So this part was not there, so we added learnable scalars alpha and beta to balance the contribution of the in degree and out degree to the alpha. And then to perform the link prediction, you can just apply a signal to a low-rank actually. So just for demonstration purposes, when I say this from index, imagine if you are node I and you're being pointed to by J, then if you want to gather the information in a message passing manner from all J's that point to you, you just multiply with the A transpose. Now, what happens though if when you're pointing to by many different J's or J in particular shows to other points to other nodes and not only you, then you have to scale, right? So basically, you take one of the three parts that J has to give. So basically, this means that we divide by the out degree of this J node. This is the page idea. And then if you have many J's that do that, say here, around you, you also have to scale with the incoming links to you, right? So you're being targeted to by different nodes. Now those nodes have an outgoing degree, but you also have an incoming degree by those that point. So basically, you start from here, and then you go here, and then you add one more scale because you scale the incoming connection, right? And so you end up with something like this that is almost a graph convolutional network if you add self-links and if you scale. Now you do the same exactly for the outputs, right? So there's some duality. This is what I'm going to do. So when you show to someone and you don't consider what is in the incoming links, but only the outputs, when I now point to J versus J point to Y, you multiply with A, because that's matrix A shows the output right? And combining this, you can the hits right here at the distance. Where you have J and I J, and this like that. So this is connected. If you keep doing this, then the same information will go to the dominant. Element of this matrix, and then a transpose the Veron. And okay, now combining all these again, the method passing from incoming links, outgoing links, and then the hit idea, you start forming big guy, right? Directly. So, like I said, the idea now is that you have source and target vectors. So if you're being targeted from I, for example, right? You have to update your target vector because you are the target from all the sources, from all the eyes. So you gather. Okay, let me actually go to the slide. So if you're here, it's the same principle, right? Your TI, right? Must be dependent on the S stage. So you have two other embedding stages. You don't have one because now you're directed to another one. So basically, you update your target, the target vector that belongs to you, by the sources, by the source vectors of the node, the point. And so you do this, and then if you write it in a matrix notation, you end up with something like this, which is the encoding part, right? And then you decode by for the idea by taking the rank one actually the rank K updates. Actually, this is a better slide. So to reach the direct graphical encoder by leveraging ideas from the graphical network entries, this is just a simple representation. You take your transit matrix, you add a self-reading by the identity matrix there, and you do the same the increase and the output. So that's why from the B plus and B minus matrices are probably the output B plus shows the output in the diagonal, then B minus shows the input from the diagonal, which is a diagonal. So you add the identity, you add the things, and then you scale by alpha and beta. And then you end up with an A-hat matrix, right? It's again the scale based at the cyclical data matrix. And the first layer, not even a non-linear at all, right? You just do straight embeddings even before the neural networks. So you don't need non-linear. So you just multiply the advanced matrix. You have the PWP and SWP, so WPW is other than the matrix. You have a loss function again, not even non-linear. There is a way to differentiate it. And then you have a signal of some other non-linear function of choice, and then you form this matrix on the embeddings that you took from one layer of DI, and this gives you probabilities about connections. It's asymmetric because this is not asymmetric. Again, for the direct case, for the undirected case, you will have the same here. And you can generalize this to multiple layers by just adding non-linearity. Here we have the two-layer example. This one has a non-linearity embedding. When you basically do what we did earlier, you apply a non-linearity to the rectangular matrix again, and then you have another layer. Then on top, you have four matrices in the top. So run graph, direct graph over the direct graph of code basically leverage. At the time, the paper leveraged for the first time this idea of source and target vectors for from a graph convolution layer, graph convolution network perspective. And before I go to the experiments, well, there's not much theory to accompany this idea, right? However, there are parallels with the Weisfeiler-Leman test for graph isomorphism. So basically, the reason why this the Weisfeiler-Leman is actually the test. So why one layer DNS and one WL are related is because you have the class functions, right? So when you apply the Weisfeiler-Leman method, you got isomorphic. You has something your neighbors. So this is where it counts. So I am here, you point to me, so I take my label and the labels of the node that point to me. I has it, like come with a new label, and that goes on and on. And this idea is similar to the graphing identity in the sense that I consider my source vector, actually my target vector, and I take your source vectors, and I basically do. So if you unknown this to a bipartite graph, basically you can apply a panel to the Weisfeiler-Leman via two directed networks by just increasing. If you have 10 nodes, you have a 2n bipartite under the network. Basically, you can draw the same parallel. This is not useful for the actual implementation. It's just a parallelism that is interesting. And numerical experiments, so the hyperparameters outline data, I will think like we have research, also the values in the next slide. We initialize the input, which we are getting the dominant, let's see the vectors, okay, 16 dominant, let's see the vectors. For some, the paper has more larger data sets. Here I also deploy the sites here and those are citation graphs and ancillary and other disciplines. We also have classes of all of them, but this is very important. So some statistics about how we train the network, and what we use for validation and testing. So okay, I mean one takeaway message is that even something as simple as just putting the alpha and beta scalars and attaching different importance to the outgoing and the incoming can lead to performance variation. Now, larger values of alpha and beta, for example, when alpha goes here, beta goes here. So larger values over 100 degree contribution, right? Because they boost the degrees, so the diagonal needs to degrees. So they generally put smaller values to the certain target encodings, and then if you apply the sigmoid, actually many things have still small values, so you basically do not predict things very well. So that's why, and actually this is in the good case, in the paper in the appendix, you can see that when you have both alpha and beta large or small, you go to the performance to the alpha and beta right, performance degrades. It seems that the best results are for around alpha and beta are about a half, 0.5. Surprisingly, this is true even for models in recommender systems when we do something similar. There it seems that a small positive value was also the best performance. And then small values of alpha and beta under right? So they generally mean larger spectrum intervals. What I mean by that is that so the blue, orange, and green line, right? They have alpha and beta to 0.5 and 0.8 respectively. So basically, when you use small alpha and beta, you just kind of compress all of the information into a bunch of directions, and that is not thought out very well. Right? So on the other hand, if you have 0.5 for both alpha and beta, this is true, right? You have a smoother picture. But in any case, smaller alphas are important for all of the coding to make the connection, right? For coding, they formed by I, and then smaller values of beta are reinforced by all of alpha. So basically, why it works is because you can tune during the network, during training, can tune the network to give higher consideration to different things. And let me see. Okay, and just to conclude this part, here is a table against some other ideas, gravity. I think gravity and source target are in the same paper. Gravity introduces the concept of vertex mass, while source target is something less That's refined with graph advance. It uses an embedding of size 2 for its node. It stacks assertion and direct vector at the same training base. So basically, this is the one that is the most powerful to direct graphical encoders. Well, you will notice that the part without even the non-linear attached, that's slightly better. It's not always the case. However, depending on the problem, you might not even need the full-blown part of neural network, and kids like idea might look fun. And I'll go quickly through this part. So the quantum graph transformer, right? So the idea here is that you want performance graph analytics using AI models. Sure. Okay. I mentioned we talk about graph transformers. We work on graph transformers. That was the original talk that I was planning to talk about. But to do that in line restriction and then something else. This paper, I think this work, published at ICAS last year, and well, the idea is to take the graph transformer architecture and map it to a quantum computer. Now, when I say map it, I have to admit that I'm very optimistic, right? I mean, and almost everything that I'm going to talk about could be done and implemented in a very, very different way. So I say quantum graph transformer, but take that with a pinch of salt because the topic is far from here, and I mean, too complicated. So why do you want to try graph transformer? Because because due to the attention, you have all-to-all connectivity. Right? So you can discover latent connections that are not yet are not there by structure enforced from the advanced metric. So they can potentially give better performance in terms of accuracy, how you train them, and how long it takes. That's a completely different discussion, right? So at the time, I'm not even sure now. There was no related work, so we said, okay, maybe we can try it. Quantum computers now, I don't know how many of you are familiar. They are just non-classical computing paradigm, right? That they don't use bits 0 and 1, they use qubits, which can be in a superposition of 0.1. So basically, you can be anywhere in a sphere, and by virtue of that, they can supposedly compact and transfer much higher volumes of information. Their post-quantum architecture means they don't have memory. They carry information and compute on the fly. So the memory element is also this. Now, what you need to know is that no matter how tough it is to deal with the notation or the architecture or hardware or devising sustainable algorithms for these devices, what they are really is matrix vector engines, and basically they take a state and they apply gates, which is nothing else than unitary matrix vector products. So they transform an initial state to some other state, right, that you don't know, but you can measure collapse essentially, and that's it. And by saying measure, the moment you open a quantum computer, so to speak, you don't know what was in there, right? So basically, you have a quantum state that you will have to collapse to 0, 1, 5 bits in the end. However, this is very probabilistic. You don't know if you will get 0 or 1. It depends on the output, so you never know. So you have to run the experiment again and again and again. So I'm not going to go through all these details. However, if you want to do a proper study of quantum graph of quantum graph transformers, the subject is basically accuracy. So and so we'll try to do a first exploration. So I say that what we're going to discuss next is part from exact science, and what I mean by that is that while sound, many things can be designed in a different way, right? So the idea that you have in graph transformers is you start with a graph abstraction encoding, right? That you are embedding a picture vector that you have some positional encoding as well. And then you have the attention, right? So this is graph transformer 1, graph transformer 2. Then when you go to the quantum part, you have to encode this graph structure, right? The initial embedding with a quantum circuit. And then you also have to do the attention mechanism, right? And obviously, there is no attention mechanism in that computer. So we use a variation of parametric gates. So you have the parameters here, right? So here you have positional encoding and global attention gates. And then you mark the one part of the encoding part and then the variation of one attribute. I'll just say it and how do you encode the first part? How do you encode the quantum circuit? Well, I don't know. I mean, we don't know what is interesting, right? But what we know is that we can start from the ground state and then apply some random gate, which means randomize your initial entry. So you just randomly flip things, right? That's all. Like a random market distribution in a sense, where you have entries plus minus one with equal probability, right? And then you apply some gates, some quantum gates that basically what they do is they just change the phase at random. So you basically start from something deterministic and you poke it. You just add randomness, right? To create some, to create some initial encoding, and then once you have that encoding, you try to do what the transformer does, right? You try the attention part that is all to all. So you have a circuit that you connect every qubit to each qubit to every other qubit. You add some parameters there that you need to learn, and that's basically the attention. And how you do that? You just add some angles around the y-axis. You just try to do that. So to make things more clear, you start with a graph with 6 nodes, right? And this connectivity. In this particular case, it's undirected, but it can even be direct. So you have the encoding sequence, right? So you have 1 qubit per node. So you have 6 nodes. You have 6 qubits, and then you enforce the structure dictated by the graph, right? So in other words, let's see, 0 is connected to 1 and 5. So you see connection to 1, qubit 5. So here are the Hardeman gates for the randomization part. And then you have the connectivity by having 2 qubit gates as controlled by the network itself. So you do a forward pass for the encoding part, and then you have the variational circuit where you have the gates, different gates with different theta angles. So in total, and when I say it's probably an exact science, because when you have more nodes, right? So for n nodes, we have 2n parameters, not n squared, like a formula. However, you can keep adding angles and gates and see what comes up with. It's not clear how exactly you should, but we found that this approach was the best. Basically, this picture you encode your graph with a single vector. It's not a vector, it's a quantum state embedding, which then you go and pass through the network. And here you see all connections, right? So all qubits are pairwise connected. And again, another example, just the full pipeline. So imagine that you have just a triangle, right? You encode it, you encode the connection, you go through the quantum state, right? Which something like this, plot it. I mean, you cannot plot it when you actually run it, but you simulate it, do something like that. And then you have the variational circuit, and then your variational circuit will go and be in one of the 2n. So for n qubits, you have 2n states, right? And then you measure at the end. However, you measure only probabilistically because you don't know at what state its qubit actually is. You can only sample again and again and again. So that's how quantum mechanics work, right? So it's nothing about AI. However, having this two-phase transformer, so you have both things at the transformer phase. You have embedding and then all-to-all. How you implement them in a quantum computer? We implemented them with the two different circuits. And so here are some really toy examples. Reminds them that you have so you have 2n states. So you have 1,000 nodes, it means you have 1,000 qubits, which is this idea. And you have 2 to the 1,000 states. It's impossible. Right? So the idea where you have 1 node per qubit needs some work. So, however, it's a start. So now we did graph classification, right? And the idea is, does the graph have a triangle? Click of 3 nodes. This one has, this one doesn't, right? So if it has, it's a label 1. If it doesn't, it's a label 0. And you want to understand whether the graph that I'm giving you belongs to class 0 or 1. I just have to mention that you can do domain decomposition and graph decomposition. So you don't even need a quantum computer that can handle the entire graph, because then for the triangle counting protocol down, you can, and there are specification techniques, or you can even sample subgraphs and then decode the skeleton and then do graph matching, right? I mean, if you know that certain graphs have a certain number of triangles, then you can do structural matching that you can easily do with a quantum computer and say, okay, I'm 90% similar to a graph that has 5 triangles, so maybe I have 90% of 5 triangles. So anyway, so we evaluate the training performance in terms of training loss and upwards precision, and well, the evolution of training, right? Clearly, it's not rapid. However, it does show that you can actually learn something. You do, like with that quantum circuit. I mean, basically this, right? That you try by doing this encoding and then by having rotate y-axis rotation right in the beginning and then at the end, it actually learns something meaningful. So it imitates this. So imitating this transformer, graph transform idea to a quantum computer can give you something. And let me see, this is the last slide. Yeah, I mean, so these are some different cubic, actual hardware cubic topologies that IBM has, and we map the software. All this was done with KISS, right, with a Python simulator, and to these different architectures. And what initial other precision shows is that we took some slightly boosted random choices. That's why you see it fluctuating around 0.5, because we started with some angles that were giving something better than 0.5, and then you have you incorporate the angles of what you learned with the quantum graph transformer, and you go close to 1. Admittedly, the problem is not really tough, but it shows that you can actually learn something. And I don't know if other people have tried it. I mean, the quantum computing thing is, I mean, IBM supports the process. So we have quantum computers at IBM, so. So yeah, that was the main idea. So that's all. Yeah.
Thank you. I do want to say if you man, they want to problem this. Manuel also works on the directed graph in one of these. I think there are some similarities between your work when you, because in their work they are introducing the, let's say, one direction, so they learn in one direction and you do other direction. So you define these architectures. Yeah.
Yeah, I mean, you're separating the source and the destination embeddings, right? Which is the idea. Our work, which was actually published a lot of years on your work. It's kind of an extension of MPNN where you basically aggregate in both directions, and you have different weights, but then you kind of put only at one vector for each node, so we don't separate. But it's interesting. When you look at classification, whereas you look into prediction.
Yes.
Yeah. So probably for the predictions, it's more important to separate, right? Which then you can.
Yeah. So then why we started trying it, because it cannot be done to that extent. So we took the hits idea and we were both familiar. I mean, all of us were familiar. So we said we tried it. Yeah, trying it kind of started to make sense by its, in the sense that you could pick up some signals, right, to do the task. But yeah, I mean, what this is, yeah, that's it.
I really like the idea of, I think it was, if I remember correctly, it was your paper proving of that if you split the basically, theoretically, if you have a graph of 2 nodes for each node, right, then you can represent any directed graph with non-directed graph, double the number of nodes, right?
Yeah, for the WL.
Yes.
Yeah, that was a paper from, so the original connection from paper in 2019, right? And yes, we actually thought about how to do that, and the idea with the double passing, and eventually, because if I am source and you're the target, if I do WL directly to the case, it's like I'm mixing source and target. So we said, yeah, let's just have 2 times the nodes and the both.
Any other questions? So I also have these quantum graph transformers. Are you looking into, let's say, the expressivity of the, let's say, hierarchy, or
Yeah,
does
so
it make sense to also extend these
yeah,
ideas to quantum graph transformers?
in principle you should. I mean, if you simulate the thing, maybe not that much. But if you were to actually be serious about it in the future, like actually, if science takes us there, right, then you can use quantum computers for this class, you will have to do what you say, because if not, then the whole system you are wrapping together will be quickly unstabilized. So quantum computing, like you have to do things rather rapidly, right? Because then there's something called the coherence, and the cube itself becoming unstable, right? So you have to maintain it at freezing temperature, almost 0. So I think learning, yes, in practice, as a good method of doing things, if you were to ever be serious to implement them, double yes.
Great.
Thank you.
Thank you. Thank you.